Hello and welcome to the third and final video of the FP1 chapter, Coordinate Systems. On the screen, a quick question to review differentiation because we're going to use this in this video. Pause the video now if you've got time, give this a go, and I'll do it on the screen here. Find the equation of the tangent to the curve this at the point P216. So to find the equation of a tangent, first we need to find the gradient at that point on the curve. To find the gradient, we need to differentiate the equation for y. So the derivative of y with respect to x is 6x in this case, that is it. Then we need to evaluate this at the given point, because this is a gradient formula for the entire curve, but we only want the point where x is equal to 2. So when x is equal to 2, dy by dx is equal to 12, and this is the m in our straight line equation, which we can now use. Y minus y1, the y coordinate at the point is 16, equals 12, x minus x1, which is 2, and then we can put that in whatever form we like. In this case, I'll put it in y equals mx plus c form, so here we've got a minus 8. And this is the equation of the tangent to the curve at the point P. If we wanted the normal, the only thing we would do differently would be to use this equation m1, m2 equals minus 1. And here, the gradient of the tangent would be m1, the gradient of the normal would be m2, and so the gradient of that would be minus 1 over 12, and then you do the same process here. Stuff you've done before with different functions. In this video, we'll be doing it with parabolas and rectangular hyperbolas. So we've done parabolas, we've looked at parametric equations, now we're going to do rectangular hyperbolas specifically, and then we'll go into the tangents and normals pretty quickly. As with the previous video, there are a couple of additional examples between exercise 4D and 4E, so I've put them at the end here, although there's no new concepts. So the two curves you need to be familiar with, I've already said before, one is parabolas. We have all this information from the last video, the parametric equations, the Cartesian form, the idea of a focus and a directrix as a locus of points, and the second one then is the rectangular hyperbolas. We have met this already in the first video. We saw that it was a 1 over x curve with these parametric equations. X is equal to ct, y is c over t, where t is not equal to 0 because of this, and c is a positive constant, just like the a up here. And we saw that it gave us this graph here, and if you divide by x, that's why it's a 1 over x curve. Now you might immediately ask, well, what about a focus and a directrix? There seems to be some similarities here, what about this bit? And that would be a very sensible question. There is a focus and a directrix for this curve, but we don't need to worry about that. If you do the FP3 module, you will look at hyperbolas more generally, and you will look at focus and directrix for hyperbolas, but a rectangular hyperbola is a very specific type, and although we do use them, the focus and the directrix is a little bit more complicated for this, so we tend not to worry too much about it in this course. You've got some of that to look forward to if you do FP3. But for now, you just need to make sure that you're familiar with this for parabolas and with this for rectangular hyperbolas. And that's about it for those curves. We're going to look now at the tangents and normals to these curves. And as we had on the starter question, you know that to find the equation of a tangent or normal, you differentiate the curve, apply m1, m2 equals minus 1 if you want the normal, then use the gradient of the tangent or the gradient of the normal in the straight line equation, this or y equals mx plus c, whichever one you prefer. And this is exactly the same process for any curve. The only difference is that it can get more complicated to do the differentiation the more complicated the function gets. In this case, to differentiate parabolas and rectangular hyperbolas, we can either use implicit differentiation. Don't worry if that is unfamiliar to you, that comes later in the P4 module. But if you know how to do that, then you can do that. Otherwise, you can use parametric differentiation if you've done that. But don't worry if you haven't, because otherwise you can rearrange the Cartesian form and be careful of any plus minus signs. Now, because you haven't necessarily done these before doing this module, the one I'm going to use in this video is the last one. We're just going to rearrange the Cartesian forms to give y equals, and anywhere there's a square root, we're going to be very careful of the plus minus signs. And the rest of the video is just going through examples. Here's the first one. The point P, where x equals 2, lies on the rectangular hyperbola h with the equation this. So c squared is equal to 8, so c must equal 2 root 2. Find, giving your answers in the form this, where you can assume a, b, c should be integers, the equation of the tangent and the equation of the normal at the point P. Okay, this is very, very similar to our starter question. The only difference, as I said, is the differentiation of the function. So to differentiate this, first we need to rearrange. We need to make y the subject to do the method I'm going to do, which gives us this equation. Differentiating this gives us minus 8x minus 2. And that's it. If you want to write that back in this form, we can. So that's the gradient function. To find the equation of the tangent, I need to use this where x is equal to 2. So dy by dx is equal to minus 8 over 2 squared, which is 4, so that's minus 2. And because this is so closely tied with part B, I'll do part B a little bit by the side here, because here the gradient is equal to minus 1 divided by that. So we have a half. Back to A, the gradient here is minus 2. So now we're using y minus y1. Now I haven't calculated this yet. Let me quickly do this at the top here. We have x, y is equal to 8. So if x is equal to 2, then we've got 2y equals 8, and of course y must equal 4 at this point P. So y minus y1, which is 4, is equal to n minus 2 times x minus x1, which is 2. And we want it in the form ax plus by plus c, so I need to rearrange this a little bit. We've got minus 2x plus 4. So we have 2x plus y minus 8 equals 0. And that is the gradient of the tangent. Now let's continue with the normal. Very similar. Y minus 4 is equal to a half x minus 2. So we've got 2y minus 8. If I multiply everything by 2, x minus 2. To put it into the form that they want, we've got 2y minus x minus 6 equals 0, and that is the equation of the normal. Example number 2. The distinct points. That's telling you that these are two separate points. A and B lie on both the line x equals 3 and on the parabola C with equation this. So a quick sketch. I do like my quick sketches. Here's our parabola, something like this that goes through the origin, and then x equals 3 is over here somewhere maybe. And they're telling us that points A and B are distinct points. That means one of them is this one and the other one is this one. So the line L1 is tangent to C at A. We don't know which one A is, but let me say it's this one for now. And the line L2 is tangent to C at B. So I've made an assumption here. I might have to flip these around if it's important later and I've chosen them to be the wrong way around or something. But for now, I've sketched it so I've got an idea of what it looks like in my head. Given that at A, y is greater than 0, I should have read the full question. They're telling us that the y coordinate is positive at A, so I have chosen them the correct way around. That's handy. Find the coordinates of A and B. Okay, so the coordinates of A and B are quite straightforward because we've got the equation here of the parabola. We know they're both on the parabola, and we know that they both have an x-coordinate of 3. So I just put 3 into here, and find y. So when x equals 3, y squared is equal to 81, 27 times 3. So y is equal to plus or minus the square root of 81 plus or minus 9. And that's one point where we need to be a little bit careful to remember that we get two answers out of that. It's easy to remember in this question because we need two answers. So A is the positive y value, so that's got coordinates 3, 9, and B then must have coordinates 3, minus 9. Part B, draw a sketch showing the parabola C. Well, I've already done that. Indicate on your sketch the points A and B and the lines L1 and L2. Yes, I've got all of those on there. So again, as part of my process, I've already done that bit. Part C, find an equation for L1. L1 is the tangent to this curve here, where x is equal to 3 and where y is equal to 9. Okay, so we need to do what we always do. We need to differentiate this equation. This is where implicit differentiation might help you if you've done that, but assuming you haven't, we need to square root this. But what's really important here, and what your implicit differentiation won't have a problem with, is that we need to remember to put a plus minus on this. So differentiating this, I'm going to keep that plus minus there. One of these is working for A, and one of these is working for B. So I'm actually doing both of these together in terms of the differentiation because of the plus minus here. That covers both of these. So I'm going to write that as plus minus 3 root 3 times x to the half, so that I can differentiate this more easily. The half comes down, so we have plus minus 3 root 3 over 2 x to the minus half. So that covers both C and D. Now we need to be more specific. So for C, I'm going to have the gradient is equal to the positive root. So we've got 3 root 3 over 2 times x, which is 3, to the minus a half. So that's 1 over the square root of 3. So the square root of 3's cancel out. And my gradient is 3 over 2. Then I put it in my straight line equation. Y minus y1, which is 9, is equal to 3 over 2 times x minus x1, which is 3. And they haven't told me a specific form to put this in, so I will stick with what we had in the previous example. So 2y minus 18 is equal to 3x minus 9, which gives us a final answer of 2y minus 3x minus 9 equals 0 for the equation of L1. Okay, last part is the equation of L2. Now this is still a tangent. L2 is still a tangent, but it's the negative tangent down here at point B, so I need to take the negative version of this. So it's negative 3 root 3 over 2 times the x coordinate at B, which is 3, to the minus a half. So again, the square roots cancel out, and we have minus 3 over 2, which is the m for our line. Put that into the straight line equation. In this case, we've got y plus 9 because it's minus 9 for point B is equal to minus 3 over 2 x minus 3, 2y plus 18 minus 3x plus 9. So we have 3x plus 2y plus 9 is equal to 0. And that is the equation of L2. The key thing here to realize from this example is that if you're going to differentiate in Cartesian form, and you're going to do it by rearranging rather than implicit differentiation, then you must have the plus minus on here, because it's doing 2 points at the same time. And then it's a good idea to have a sketch here so that you know which one is the positive gradient and which one has the negative gradient. That's very important. Third and final example before you can attempt exercise 4D is this one. The point P with coordinates this lies on a parabola C with equation this. Find the equation of the tangent to C at P. giving your answer in the form y equals mx plus c. This is a very similar example to the last one, if anything a little bit easier. We've only got 1 point to worry about. We need to rearrange this to give, remember, the plus minus root 12 x to the half. Differentiating gives us plus minus root 12 over 2 x to the minus a half, and then we've got x is equal to 3, and that gives us the gradient of plus minus root 12 over 2, 3 to the minus a half. And in this case, the 2 here, if you make that a 4 and put it in the square root, that cancels to give us a 3 inside, and then this is a square root 3 on the bottom, so they cancel, and we end up with a 1. And now we need to have an idea of what the graph looks like in order to choose which of these two is the correct one to use. And we know this because the parabolas we're using always have their vertex going through the origin. So 3, 6 must have a positive gradient. So we're using m is equal to 1. And then into the straight line equation as usual, y minus 6 is equal to 1 times x minus 3. So y is equal to x plus 3 in y equals mx plus c form. So this is the point where you can stop and do exercise 4D, or if you prefer, you can continue watching the final 2 examples that will lead you into exercise 4E as well. The point P with the general coordinates this lies on the parabola with equation this, where a is a positive constant. Show that an equation of the normal at P is this. So we're going to do this in a very general way. These, you'll notice, are the parametric equations. The x-coordinate is at squared, the y-coordinate is 2at. That's quite a common way to write it. If these are the general parametric equations, then of course the Cartesian equation is the general Cartesian equation. So we're going to do the same as we've been doing. In this case, we're going to rearrange to avoid using implicit differentiation, and that gives us this, which I'm going to rewrite as 2 root a x to the half. Differentiating this, the half comes down and cancels with the 2, so we get plus minus root a x to the minus a half. And at the point P, the x-coordinate is a t squared, so our gradient here is going to be plus or minus the root of a times at squared, all to the minus a half. So if I make that a little bit more obvious what I'm doing by putting that in square root and fraction form, we've got square root of a on the bottom, and we've got the square root of t squared on the bottom, which is just t. So you can see that these will cancel, and what we end up with is plus or minus 1 over t. Now I've kept this plus minus in here to be really clear that this is an important step when you're doing this, but actually in this example, whether this is a plus or a minus depends on the value of t. So I don't need it in this case because it is already hidden within the t value here. So the gradient for the tangent would be 1 over t. And the gradient of the normal, which is what we want, is minus t. And that minus there is still very important. We can put this into our straight line equation, y minus y1, which is 2at, is equal to minus t times x minus x1, which is at squared. And hopefully, when I expand and simplify this, I can get this. So I have minus tx plus at cubed, and over here we still have this. So if I bring the minus tx over, we get y plus tx, and the minus 2at on this side, we get 2at plus at cubed as required. Final example in this chapter, we have the point P with parametric equations of a rectangular hyperbola, where t is not 0, obviously lies on a rectangular hyperbola, h, with equation this, where c is a positive constant. So again, we're doing this very generally. Show that an equation of the tangent at P is this. Then we have a second part, but I'll do a first. So we need to show an equation of the tangent at P. To do that, we need to do all the things that we've been doing. So let's rearrange this, c squared x to the minus 1, so that we can differentiate, minus c squared x to the minus 2, and then put in the x coordinate. In this case, x is equal to ct, so dy by dx is equal to a minus c squared over x squared, which is ct. So our c squareds cancel out, and we have minus 1 over t squared. And this is the gradient of the tangent. Putting this into our straight line equation, y minus y1 c over t is equal to minus 1 over t squared times x minus ct. And again, if I expand and rearrange, hopefully this will take me to the equation they want. First, I'm going to multiply everything by t squared to get rid of those two fractions. So we get t squared y minus ct is equal to, expand this out now, minus x plus ct. Bring the x over and bring the minus ct on the other side, gives us 2 lots of ct as required. Okay, that is the equation of the tangent. Now on to part B. The equation of the tangent still here, if we need it. A rectangular hyperbola G, where h was our general one, G has the equation this. The tangent to G at point A and the tangent to G at point B meet at the point minus 1, 7. Find the coordinates of A and B. Okay, first of all, let's look at this. We know that xy equals c squared is the general rectangular hyperbola equation. So if c squared is equal to 9, then c is equal to 3 in this specific case. We also know the general equation of the tangent to a rectangular hyperbola because we just found that in part A. So we don't need to do the work all over again. The tangent at the point A has this equation, and the tangent at point B has this equation as well. But of course they have different values for t, although they both have the same c. So how are we going to solve this? Well, let me write out the things that I know. At point A, we have a tangent x plus t squared y is equal to 2 times c times t, and we know c is 3, so we've got 6t. We also know at B the same thing is true. Now it might seem like we need to find the value of t to distinguish these two, and that's true, we do need to find the value of t. But we're using the fact that they're the same in order to do that, because they meet, this one and this one meet at this point here. So we're told a point that is on this line and is on this line. So I can put these coordinates in either one of these and it needs to be true, and that will tell me the value of t. Which might seem strange because I should have 2 different values of t, one for point A and one for point B, but this is a quadratic in t, so we will get 2 answers when we solve it. So whether we sort of say we're solving this one or we say we're solving this one, it's the same obviously, but whichever one you were to choose, you would get 2 values, and one value is for A and one value is for B. So I'm going to put it in and see what we get. X is minus 1 at the point where they meet. T squared is the thing we're trying to find. Y is 7 at the point where they meet, and this has to equal 6t. And this is true of both tangents, obviously, because they're the same. So we have 7t squared minus 6t minus 1 is equal to 0, and because of that 7, I think this will factorize. So we've got a minus 1 and a plus 1, which gives us the answers t is either equal to 1 or t is equal to minus 1 over 7. Now I don't know which one of these relates to which point. We don't have enough information in the question to say that this has to be A or that this has to be B. But that's okay. We just follow through and we need to find 2 sets of coordinates, one of which would be A and one of which would be B. Now we've got the value of t, we should be able to find the coordinates because we know the parametric equations ct and c over t, and we know c is 3, so for one of these 2 points we have the answer 3 times 1 and 3 divided by 1, and for one of these points we have the answer 3 times minus 1 over 7 and 3 divided by minus 1 over 7. And like I said, we can't be sure which one is which, but either A or B is this, and then the other one is this. And that is the final example of this chapter. You can now practice the concepts in this video from exercise 4D and 4E, and also the chapter review exercise for all of this chapter, but also we hit the middle of the textbook, and there's a big review exercise 1 that covers all of chapters 1 to 4. And maybe I'll see you in chapter 5.